In this video, we're going to talk about gas volumes. Now, specifically, we're going to talk about the molar gas volume, which is 24 decimeters cubed. And we're going to talk about how you can use that number to calculate the number of moles of different elements within an equation. And we're going to go over a couple of example questions in the process. So what is molar gas volume? So molar gas volume is, first of all, 24. And what it means is, at room temperature and pressure, which is RTP, if you recognise RTP, if you see RTP, okay, that means room temperature and pressure. Room temperature is usually about 20 degrees, room pressure is about 1 atmosphere. But if you see room temperature and pressure, 1 mole of any gas is equal to this 24 I just said. So 24 decimeters cubed, really important you know the unit. And that means there'll be 24 decimeters cubed of that gas per mole of that gas. So remember it's 1 mole, so it'll be 24 decimeters cubed per mole. Now, decimeter, 1 decimeter is 1,000 centimeters cubed. So if you want to go from decimeter to centimeters cubed, you have to times by 1,000. And if you're timesing by 1,000, here you can say 24 times 1,000 is 24,000. That means 1 mole of any gas at room temperature and pressure will be equal to 24 decimeters cubed or 24,000 centimeters cubed. Now, what's not gone over in textbooks often and can appear in exams is this also leads to the following. If you have the same volume of any gas and then you make that gas have the same temperature and pressure as other gases. So for example, if we had oxygen and nitrogen and we said we're going to have 20 centimeters cubed of the oxygen, 20 centimeters cubed of the nitrogen, and I'm going to set the temperature and pressure of both of those the same, they'll have the same number of moles. So if you know the volumes match, you can then say, and you know the temperature and pressure matches, you know the moles will also match as well. But let's look at this pictorially. Let's just say I set my temperature and pressure. So I've set my temperature and pressure to 400 and 100 kilopascals. Okay, and then I take 3 samples. So I've got neon, and I have oxygen, and I have water. Now these are not to scale, so if you're looking at the number of balls we have, or molecules, elements or molecules we have, okay, they're not to scale. They're just simplified to help you understand. But as you can see, there's the same number of particles in each one, which theoretically means there should be the same number of moles in each one. We've set the same temperature and pressure, so we've got the same number of moles because there is the same number of particles, same temperature, same pressure, which that means it will have the same volume. So let's just say that volume is 120 centimeters cubed, and therefore all will have also 0.1 moles. Again, it's not to scale, so don't worry about doing the calculation on the numbers. We're now going to do an example question on molar gas volume. Now to do this, we need to use a couple of equations. Now hopefully you should become familiar with, or be familiar with, moles equals mass over mR or AR. Okay, most commonly used equation in chemistry. Now if we then go from here, we learned another new one. You probably haven't realised that yet, but if you look here, we've got moles equals gas volume over molar gas volume. Now we know that 1 mole of gas at RTP, so this only applies at RTP, only applies at room temperature and pressure, is 24. So if that is the case, you can work out your number of moles times 24 would be your volume. So if you just rearrange that equation, that's moles equals gas volume, the volume of your gas, divided by the molar gas volume. And we can simplify that down even more and say, what is the molar gas volume? The molar gas volume is 24. So what we're going to do is we'll use the 24 instead throughout the next calculation. So the example question is when you have a mixture of powdered zinc oxide, and here's your zinc oxide down here, reacting with carbon, turning to carbon dioxide and zinc. And the powdered zinc oxide was heated with excess carbon. Excess carbon means I don't have to worry about the moles of the carbon because there's just far too much of it. The limiting reactant is therefore the zinc oxide. Now we want to know the volume of gas that is measured. The gas is carbon dioxide, but it importantly tells us this is at room temperature and pressure. Now that tells us the following, and will tell us the following in any question which we come across like this. If you see the term room temperature and pressure, often accompanied by RTP, you can assume 1 mole of a gas is 24 decimeters cubed in volume. Let's move that to the side. Now when it goes to the side, we'll bring the equation up to the front, and you can see we have highlighted the 2. That's because there's a need for my net answer to the question to know the ratio between the zinc oxide and the carbon dioxide. And you can see it's 2 to 1. So if you want to find out or convert the number of moles of zinc oxide into the number of moles of carbon dioxide, you need to divide by 2. But we'll do that in a second. So I'd also give you advice when it comes to this is, even if you don't know how to answer a question in an exam, do what you can do, not necessarily what you understand how to do at the time. So for example, maybe you don't understand how to do the question, but you've been given a mass. If you've been given a mass, you've got mass divided by molecular mass equals moles. So the first thing that makes complete sense is to work out the number of moles, even if you don't know the next step, and you might get 1 mark at the very least. So what we have here, and we're going to start off with, is moles, and this is our moles of our zinc oxide. Okay, so our moles of our zinc oxide, as we've got up here, is our mass, and our mass is going to be 0.407. Okay, so 0.407, and then you divide it by the molecular mass. Now we've got our symbols from the periodic table here. So zinc oxide would be 65.4 plus 16, which is 81.4. Now if you've got 81.4, put that in your calculator right now, and you will get 0.005. Now 0.005 is also equal, and I encourage you to do this, is to use standard form if you've got anything with more than 2 decimal places. So this is 5 times 10 to the minus 3. So that's 5 times 10 to the minus 3 moles of zinc oxide. Now, if we look at the ratio, it's a 2 to 1 ratio. So if I put therefore, 2 to 1 ratio, remember. So therefore, if I've got 5 times 10 to the minus 3 of the zinc oxide, there will be half of that, which is 2.5 times 10 to the minus 3. That is half of that. Okay, and that would be my moles of CO2. So that'll be my moles of CO2. So I found out my moles of CO2, and then I can use this equation up here and say, right, okay, I've got my moles of CO2, and I know that 1 mole at room temperature and pressure is 24. So just rearrange that, bring the 24 up here, it'll be moles times 24, and that will equal my gas volume. So if I take my volume, and this time of CO2, okay, so my volume of CO2, that would be my 2.5 times 10 to the minus 3 times 24. Okay, so times 24, which would equal 0.06. Now, important thing is that is always going to be in decimeters. Remember, 24 was in decimeters, so the final answer will be in decimeters. Now, hopefully at this point you remember how to convert decimeters into centimeters cubed, because we'll give you both. So if that is the case and you want to convert it into centimeters cubed, all you have to do is take the 0.06 and times it by 1,000, okay? Which means that you will get 60 centimeters cubed. And that is how you can use the molar gas volume to work out the volume of a gas, either in decimeters or centimeters cubed, when you're given the mass of the initial reactant. The next question we're going to do is commonly an MCQ question and throws a lot of people off. So it's well worth you going through and making sure you're comfortable. And there will be questions like this on the worksheet that accompanies this video, so I'd encourage you to do that as well. So first of all, it is put like this. You'll have a reaction where you have a certain volume of a reactant mixed with a certain volume of another one, which is 6 decimeters cubed of SO2 and 6 decimeter cubed of O2. And you'll also be told it's at room temperature and pressure. And it says the reaction below takes place until one reactant is used up, essentially 100% yield. Now, the reaction itself is usually given to you, so you'll have an equation like this, and then the question will just ask you what is the volume of the whole mixture, so not just of the product, absolutely everything, at RTP after the reaction has taken place. And then they'll give you 4 different answers, as you can see there. Now, if we look at the most important bits are the volumes. So let's move this to the side, as we normally do. Okay, and as it's moved to the side, you can see that there is highlighting on the 6 and the 6. So we can see it. In fact, it's room temperature and pressure. Okay, and our balancing as well. And we've repeated our equation over here because we're going to write underneath it. Now, if we look here, there's a method that works quite well, and it's used in equilibrium as well. This method is ICE. Okay. Now, ICE is I stands for your initial. So what's important is that this is at room temperature and pressure. So every single volume, if it has the same volume, it has the same number of moles. So therefore 6 decimeters cubed of SO2 has the same number of moles as 6 decimeters cubed of oxygen. So that means that 6 decimeters cubed will react with 6 decimeters cubed in terms of this SO2 and the oxygen and use up the same. So that probably doesn't make much sense unless we put numbers in front of you. So let's have a look at it now. So if we look here, we can see that there is 6 decimeters cubed of the SO2 starting off with, and then there are 6 of the O2. At the time, and we look at the SO3, there will be 0 because no reaction has happened. Then we look at this and we go, right, okay, we know this means there's the same number of moles of each, okay, because it's at RTP, and we also know that it's 2 to 1 ratio. That means that if it's 2, that means 1 part of SO2 will use up half a part, essentially, of the oxygen. That means if I have 2 moles of this, it will use up 1 moles of this. Or if I have 6 moles of this, really important, 6 moles of this, it will use up 3 moles of this. So the change, and C is the change, essentially, goes from 6 to 3. Okay, so we've used up 3. Okay, now when it comes to the SO2, if we've used up 3 of the oxygen, we've used up all of the SO2. So that means that's 0. That means at the end, that is 0. Okay, and that also means that I've used up 3, I have 3 remaining. Okay, so that means I have 3 decimeters remaining, 0 decimeters remaining of that. Now, if that's the case, remember this is the change. Okay, so the change occurring is the fact that this was 0, this SO3 was 0. Okay, but let's look at the ratio again, 2 to 2. Well, it's 2 to 2. That means if I've used up 6, so I've used up 6 here, I'm going to create 6 here. So that means the change is 6. We're using these like they're moles. Normally you do this with moles, but because it's at room temperature and pressure, you can kind of treat it in the same way. So the volume, remember, at the same temperature, the same pressure, same volume of gas will have the same number of moles. So that means we've produced 6. So just copy that down, okay? And that means at the end, I will have 3 and 6. Now, if you take 3 and 6 and you add 3 and 6 together, that will equal, okay, 9, and that is 9 decimeters. Okay, so if we then look at our answers and we go here, we got 6, 9, 12, and 15, and that means we definitely are going to have 9. So it's really, really important. 9 is your answer. Okay, and that is how you do a multiple choice question when you're given different volumes and you have to find out the total volume at the end. And I recommend the ICE method.